Delaware Tech, Chemistry 100, Chemistry 110, Amonton's or Gay-Lussac's law, and Avogadro's law. We've already talked about Boyle's law, which looked at the relationship between pressure and volume when you're keeping the number of moles and temperature constant. And we've looked at Charles's law, where we're looking at the relationship between temperature and volume and keeping the other two parameters constant. Well, Amonton, and then about 100 or so years later, Gay-Lussac, looked at the relationship between temperature and pressure. And by the way, in your textbooks, most textbooks call this Gay-Lussac's law. It is more properly now called Amonton's law because we now realize that Amonton did this work over 100 years before Gay-Lussac did. So this relationship showed a similar relationship to Charles's law. Instead of temperature and volume being directly proportional when you keep the other two parameters constant, now we have temperature and pressure proportional when you keep the other two parameters constant. So we end up with this relationship that the pressure is equal to some constant times temperature, and another way to say that would be as you increase the temperature, you'll increase the pressure. As you decrease the temperature, you'll decrease the pressure. And if we rearrange this equation, we get that this constant is equal to the pressure divided by temperature. And the reason why that's important, just like what you saw with Charles's law, is that the pressure and temperature in any one situation will be equal to the pressure over the temperature in any other situation. So we can rewrite this equation in a more useful format that gives us a before and after situation for calculating the parameters of the gas in terms of the pressure and temperature. So this equation basically says that the initial pressure divided by the initial temperature, and remember, temperature is always in Kelvin degrees when you're doing gas laws. It will not work with Celsius, certainly not with Fahrenheit. So the pressure initial over the temperature initial will equal the pressure final over the temperature final. And a lot of students find it much easier to rewrite this equation by doing what we call cross-multiplying. So if I multiply these two terms, that will be equal to what I get when I multiply these two terms. So I could really rearrange this equation and write it in a way that a lot of students find simpler to deal with, at least algebraically, into pressure initial times temperature final equals pressure final times temperature initial. And the beauty of using this version of the equation is that if you need to solve for any item, say T2 for instance, well, we could just divide both sides by P1 and you have your equation that T2 is equal to P2 times T1 divided by P1. So cross-multiplying will be your friend here. I would get used to doing that anytime you see two ratios being equal to one another. So let's look at it in practice. What is the pressure inside a sealed 0.250 liter can of deodorant that is initially at 25 degrees centigrade and 1.2 atmospheres of pressure, but the temperature is then raised to 100 degrees centigrade? Well, don't ever do this at home because this could result in your can exploding, but let's assume the can does not explode and that the can is stable at that volume. What we see right in the beginning of this question is that it's sealed. Sealed tells us something very important. It tells us that the initial number of molecules can't change. So the initial number of molecules is exactly the same as the final number of molecules. We also see that it's a can, and we're going to assume the can doesn't explode, and cans don't change volume very easily. So we know the initial volume is equal to the final volume. So the only thing that's changing is our temperature and pressure to a new temperature and an unknown pressure. So we can start by making our table that we do, and we can say we have our parameters P, V, N, and T. We know that N1 will equal N2, so this is our initial situation, this is our final situation. We know our volume 1 will equal our volume 2. So we're left with a situation where the only things that vary are temperature and pressure. That is Gay-Lussac's law, more properly known as Amonton's law. So we know that the initial pressure is 1.2 atmospheres. And we know the initial temperature is 25 degrees. And I'm writing it down here because 25 degrees is in centigrade, and we need everything in Kelvin. We also have 100 degrees centigrade for our final temperature. These both have to be turned into Kelvin. And the easiest way to do that is just add 273.3. So we'll end up with 373.15 is what I meant to say, degrees Kelvin. And if I add 25 to 273.15 degrees, I'll get 298.15 degrees Kelvin. And you don't have to worry about writing this down. This is actually all on the slide already. So I'm actually going to delete all of these notes if you've got them written. And I'll just show you that you now have to set up your equation. So we have the Gay-Lussac's law. P over T equals another P over T. We rearrange it to solve for P2. And now we merely plug our values in. We know our initial pressure is 1.2 atmospheres. We know our initial temperature is 25 degrees, so we convert that to 298.15 degrees Kelvin. And we know our final temperature, we convert that to 373.15 degrees Kelvin. Now, don't round these numbers before you're finished. Yes, if you were just asked what's the temperature, you would say 298 and 273 degrees Kelvin. But in the equation, it's best not to round until the very end. That way you don't get what we call rounding errors. So once you do put these numbers into the equation, you multiply them and divide them out, you find that the answer is 1.50186 atmospheres, which we round to two significant digits. Why? Because that has 2 sig figs, 2 sig figs. This has 3 sig figs. This has, we're going to assume there's a decimal point there, and that's 3 sig figs. So we know we have to round it to 2 sig figs in the end, and that would give us an answer of 1.5 atmospheres. Now let's ask ourselves, does that make sense? Well, we're starting from a low temperature and a pressure of 1.2 atmospheres, and we're going to a high temperature. Well, think about this. If you're increasing the temperature and you're not letting it expand because it's in a can, the pressure is going to go up. In fact, it goes up from 1.2 to 1.5 atmospheres of pressure. Let's look at a little bit more complicated situation. So let's say you start with 1 liter of gas at 1 atmosphere pressure. This is the normal atmosphere pressure you feel around you every day. And at temperature of 300 degrees Kelvin. 300 degrees Kelvin is about 27 degrees Celsius. This is just a little bit warmer than your typical room in the United States. So it's just a little bit warmer than room temperature. It's normal atmospheric pressure. And we take this container that has a piston top. So this is a top that can move up and down if we want it to, or we can lock it in place. And then we're going to heat this up from 300 degrees Kelvin to 600 degrees Kelvin. So we're literally doubling the temperature. Now you notice I said double the temperature because I'm going from 300 Kelvin to 600 Kelvin. But if I was using centigrade or Fahrenheit, I could not say doubling if I was going from 300 centigrade to 600 centigrade. That would not be doubling because remember, Kelvin starts at 0. Centigrade and Fahrenheit do not start at 0, so you can't just simply say that a twice as large number in Celsius or Fahrenheit is twice the temperature. It's just not true. But you can say that for Kelvin. So we have two situations we're going to set up. We can increase the temperature of this, and we can do one of two things. We can either keep the pressure constant, and one way to do that would be just let the piston slide up and down, that lid slide up and down, and as long as it's maintained by 1 atmosphere pressure, the air sitting on top of it is constant, just pushing down, no matter what's happening on the inside of this container. And then the other situation is we lock the lid in place. So the volume is set at 1 liter. It can't change at all. And we're heating it up. So in the first case, if we have a constant pressure, because we're letting the lid freely move up and down wherever it goes, the volume will increase in response to the heating up. That's Charles's law. You double the temperature, you're going to double the volume to 2 liters in this case. So doubling the temperature will double the volume. That's Charles's law as long as you keep the pressure constant. Whereas in the case of keeping the volume constant, that's Gay-Lussac or Amonton's law. And now it's locked, the lid is locked in place. The only thing that can change in response is the pressure inside. So now the molecules are moving around very fast, hitting the walls twice as fast, twice as hard, with twice the force for the same area, and your pressure is doubled. So you can either keep the pressure constant and you'll see a change in the volume, that's Charles's, or you can keep the volume the same and see a change in pressure, that's Gay-Lussac or Amonton's law. The third option is you don't completely lock the lid, maybe you put something on top of it, and you can let both of the volume and the pressure vary, and that would require a combination formula to solve. That's actually called the combined gas law. You can also use the fully combined gas law called the ideal gas law, but we don't generally cover that in Chem 100. We do cover it in Chem 110. So Avogadro's law is the fourth of the gas laws, and it was actually discovered last. And this was worked out by Amadeus Avogadro, the same person who the Avogadro's constant is named in honor of. And what Avogadro found was that the volume is proportional to the number of moles of gas. And when you think about that, that's really not that exciting. When we blow up a balloon, we're adding gas. We're adding moles of gas to the balloon. The volume will go up. That's going to happen because we're not changing the temperature. We're still in the same room, and the pressure outside is the same. But we're putting more air in the balloon is going to get bigger. No surprise there. N goes up, V goes up. N goes down, V goes down. And this relationship is the same ratio relationship that we saw. This is a direct proportionality where volume is directly proportional to number as long as you keep temperature and pressure constant. So V over N is another constant. Now these constants are all different constants in each of the laws, but it is a constant, and we can rearrange this equation like we did with both Charles's law and Gay-Lussac or Amonton's law. So we have the initial volume over the initial number of moles is equal to the final volume over the final number of moles. In other words, if we change how much gas is in our container, the volume is going to change too. And that's not too surprising. What was surprising, though, for Avogadro was that it did not matter what gas he put in. He used many different types of gases, different molecules, and they all showed exactly the same relationship of volume versus the number of moles. That constant between the two was always the same constant, whether he was using carbon dioxide or oxygen gas or whatever gas he was working with. So that was the interesting part. And this is actually in part what led to him being honored with the constant, Avogadro's constant, because it applies to all particles, all molecules, all atoms, etc. So this was added to the combined gas law, which you don't need to know for Chem 100, but you do need to know for Chem 110. So here is an example of an Avogadro's gas law problem. A container has 5.33 liters of gas, and that's 4.5 moles of hydrogen. It's hydrogen gas we're talking about. The temperature and the pressure are constant, so we're only dealing with Avogadro's law here. If the number of moles is increased to 7.2 moles, what's the new volume? So we have a relationship we know between the moles and the volume, and we're changing the number of moles, so we use Avogadro's formula. Here, you can actually start, if you're in 110, Chem 110, you can actually start with the full ideal gas law and just realize that since temperature is constant, well, that means T1 and T2 are the same. We can cancel those out. And pressure is constant, so that means P1 and P2 are constant, and we're just left with Avogadro's law. So this is just another way of thinking about it if you have learned the ideal gas law. So if we take this formula, and a lot of you will find it easier to cross multiply, so I have V1 times N2 equals V2 times N1, and we're solving for the new volume, that's the V2. Well, we just divide both sides by N1, and we end up with our new equation for V2, which is just shown right here. So I'm going to erase these notes, and we have the equation that we need to use, and we have all three numbers. They're all right there. We don't need to change them. Moles are in moles, liters are in liters, and we just plug those numbers in, and we find an answer of 20.3724 liters, which will round to two significant figures, or 20 with a decimal place, liters of hydrogen gas. Now we have to ask ourselves, does this make sense? Well, we started with a certain number of moles of gas, 4.5 moles, and that took up a little more than 5 liters of space. And now we're going to dramatically increase the number of moles. We're increasing it almost fourfold to 17.2 moles. Well, we would expect about a fourfold increase in volume, and that's what happened. We went from about 5 liters to about 20 liters. So it makes perfect sense. There's another problem. An isothermal, remember what isothermal means? Temperature is constant. Isobaric tank. Isobaric means pressure is constant. Isothermal's temperature is constant. Isobaric is pressure is constant. So again, we can cancel out our temperature and our pressure from both sides of the equation, and we're left with the same Avogadro's equation as before, and we can cross multiply to make it simpler again and solve for our new number of moles, which is N2. We divide both sides by V1, and we end up with this final equation. And once you have the final equation, it's really quite simple to just throw the numbers into the equation, and we put it in, and we multiply and divide it out, and we get 1.495789 moles of gas. This is neon in this case, and of course we round it to 3 significant figures here, so we have 1.50 moles of gas. Does that make sense? Well, we used to have about 20 moles of gas that took up about 90 liters, and now we have less than half the liter, less than a tenth of the liters of gas, so therefore we should expect less than a tenth of the moles to take up that space, and 1.5 is a little less than a tenth of 19.6 moles, so that works out fine. Everything makes sense, and we'll stop right here.